Okay, hello everybody. Hope everybody's doing well. In lieu of not being in a face-to-face class today, I thought I would give you a little video introduction to the next major topic that we're going to be looking at after I return first major exams to you next week. This is about tangent and normal vectors. If you think about it, we've looked at tangent and normal vectors already. Normal vectors, we saw a lot of those when we did cross products. And tangent vectors, when we looked at velocity vectors, we saw that those point in the direction of motion. So if you think about the tangent vector, thinking back to physics, they're basically the same thing as velocity vectors. But I do have a blank in here for the title, because we're going to be looking at something that's a little bit more unique. We're going to be looking at what's known as unit tangent and unit normal vectors. I think just for today, I'll just give you a little introduction to a unit tangent vector, and normal vectors we'll do next week. So again, one of the applications is velocity vectors. So if you remember, if you just do this in terms of two dimensions, so let's say we have some sort of a curve, looks like this, and maybe it has this following orientation, and let's just say that this is a representative R of t. That should be straight. I didn't make it straight. I apologize. But let's just say that a representative, let's say velocity vector, maybe looks something like this. This could be a v of t. Remember, the velocity vector has its tail at the head of the r of t. So we've looked at this before in terms of velocity vectors, in terms of the overall path of some sort of particle or object that's on this curve. Let's call it C if you like. But what we're going to be doing now is we're going to be shoring up this velocity vector so it has a magnitude of 1. You're probably wondering, why in the world do that? Stay tuned. So we're going to consider now some sort of a smooth curve. Let's just call this smooth curve. We're going to apply all of our past knowledge to finding these velocity vectors, but we're going to be shoring them up, and we're going to see some applications where the parameter is not necessarily representing time as well. I mean, most of the time, these applications and the concepts in this section do fall into a time type of example, but we'll take a look at some other examples as well. Okay, let's start with a definition. We're going to let C be a smooth curve represented by r of t on an open interval I. So this new concept of a unit tangent vector, it's denoted by this t of t at t is defined to be it's r prime of t over the magnitude of r prime of t, and for obvious reasons, can't have division by 0, so got to make sure that we have r prime of t is not equal to the 0 vector. If you look at this structure, this is the exact same structure that we had way back when we were first looking at unit vectors. Because remember, a unit vector, I think we called it u back then, that's v over magnitude of v. So we're looking for a vector, a unit vector, that's in the direction of this v, but this will shore it up so that it has a magnitude of 1. That's the exact same structure as what we have here. And if you correlate it back to velocity vectors that we had before, velocity vectors, we just took the numerator of this, so we said it was r prime of t. Now if we divide by the magnitude of r prime of t, we'll have the magnitude of 1. We'll have this thing called a unit tangent vector. Okay. Very interesting note that we're going to see towards the end of this little video. Tangent lines to a curve at a point is a line that passes through the point that's parallel to the unit tangent vector. How very interesting. Well, if you look at this through a picture, so I have a little three-dimensional coordinate system here. Let's look at some sort of a smooth curve C. So maybe it looks something like this. All right, and maybe it has this following orientation. Okay, representative r of t could look something like this. A representative velocity vector could maybe look something like this. Remember, this is the derivative of r of t. Unit tangent vector will now look something like this. Again, these two vectors are scalar multiples of each other. They're going in the same direction, but this one has a magnitude of 1, and the red vector here has a magnitude of something other than 1. If you construct a tangent line, there it is, there's your tangent line. Okay, so there's your tangent line. If you notice here, and if you guys remember, in order to form an equation of a line in three-dimensional space, you need to have a point of interest, so there's your point of interest, and you need to have a direction vector. For tangent lines, you need that direction vector has to be either the velocity vector, which is same thing as r prime of t. We saw an example of that a couple weeks ago now. But now what we're going to say is we're going to be taking into consideration our unit tangent vector and the direction numbers that this purple vector creates. So we're going to see how that shakes out in a later example. Okay? But it's a very, very interesting little concept that we can look at. Again, we've looked at the red vector with the velocity vector, which is the derivative of r of t, but now we're going to be looking at the unit tangent version of this v of t. Okay? And I'm sure you can maybe try to piece together what the unit normal vector is going to be. It's going to be acceleration. Okay, so little preview. Let's get to some examples. Here's our first example. We'll start off simply, then we'll build up the concepts as we go. So let's find the unit tangent vector to this curve. Its r of t is ti hat plus t squared j hat. When t, I just picked out a random point off the top of my head, when t is equal to 2. Okay, first things first. Let's identify the parametric equations. So we got x equal to t. We have y equal to t squared. Hope everybody agrees with that. And if you want to try to figure out what the equation is in terms of xy coordinates, you can take this x of t, substitute it back, you get something familiar. You get the parabola. All right, so here's the graph of the parabola. Okay. Again, please don't make the classical mistake of putting arrows here and an arrow here. This is a smooth curve. See, that's represented by this r of t. So this will have an orientation. And to get the orientation, if we pick out some values of t, let's say we have, we can do t equals 0. That case, you just get back the origin. Okay. So if you do this, we'll just get back 0, 0. You put t in for 0 for both of these, you'll get back 0, 0. If you do t equals, let's say our number that's in the problem, say 2, this will be 2. This will be 2 squared, which is going to be 4. So this will be here. 2, 4. I can even draw in a representative r of 2 for this if you guys want, but there it is. Okay? So I hope it's pretty obvious which way this is going. In increasing values of t, again, this is when t equals 0. This is when t equals 2. If you had a particle on this thing, it would be going in this direction. Okay, so let's find t of t, our first go around with this new definition. So t of t is going to be r prime of t over magnitude r prime of t. Okay, we need derivatives. So derivative of this is 1 I hat, simply I hat. Derivative of this, 2t j hat. divided by, we need magnitude, so we'll take square root of 1 squared, which is 1, plus 2t squared. There's your setup. Hopefully that makes sense. We'll simplify this. This is I hat plus this 2t j hat over square root 1 plus 4t squared. Okay. Hopefully that was simple enough. Let's put in this t equals 2 in for this and see how it shakes out. So t of 2 is going to be I hat plus 2 times 2 j hat over square root 1 plus 4 times 2 squared. Simplifying, I hat plus 4 j hat over square root 1 plus 4 times full, which is going to be I hat plus 4 j hat over, this is 16 plus the 1, so it'll be square root of 17. Notice we can write this as a scalar multiple, so it'll be 1 over square root of 17, scalar multiple I hat plus 4 j hat, which this will boil down to be, if you distribute out the scalar, this would be 1 over square root of 17 I hat plus 4 over square root of 17 j hat. So we found our unit tangent vector, and hopefully you all believe me that it is a unit vector. I mean, if we quickly do this in our heads, if we take the magnitude of this, are we going to get 1? Yes. Just doing it quickly in my head, yes we will. I have no idea what these decimal approximations are, but to make a little sketch of what this vector would look like on this picture, again without having graphing paper, maybe something that looks like this. So this would be t of 2. There's your little tiny unit tangent vector at that point. All right, that's the first example. Simple enough, I hope. This formula looks pretty innocent based on this one little example. But depending upon the example, and of course what the vector value function is, the algebra for this could grow exponentially. So we'll see some examples on how algebra can be a little bit cumbersome when it comes to this formula, and then we'll also see how it can be a little cumbersome when we get to the unit normal vector next week. Okay, but let's take a look at this next example. This will just be straight up finding unit tangent vector, no graph, because there's an interesting little twist of events that occur in this algebraically that I want to review with you for things that are coming up. Okay, so find the unit tangent vector of this r of t. You got t squared, you got 4t, and you got 4 natural log of t when t is positive. We want this thing to be positive because that's when it's going to be smooth, because of this issue with the natural log of t. Okay, so let's copy down the formula. T of t is going to be r prime of t divided by magnitude of r prime of t. Okay, let's start finding derivatives and see how this will shake out. Okay, derivative. Okay, this one, 2t. This one, 4. This one would be 4 times 1 over t. I'll write this as being 4 over t. Divided by the magnitude. Okay, so square root of 2t squared plus 4 squared plus 4 over t squared. Hopefully everyone's following along. This is going to be 2t, 4 over t. Numerator is pretty much going to stay the same for the time being. This is going to be divided by square root. Okay, laws of exponents. This will be 4t plus, 4t squared rather, 4t squared plus 16 plus 16 over t squared. Okay. Now, I think we can try to factor the stuff that's under the square root. So in other words, the stuff that's the radicand. And we can factor this, but we have to recall something from algebra. I'm going to do this over here. We have to recall our special factors. Special factors. And there are 2 of them. Okay, so here's the first one. Take a plus b, quantity squared. That's the same thing as saying a plus b, But if you FOIL things out, you're going to get a squared plus 2ab plus b squared. And the other one, just a subtle difference, is if you have a minus b, this will be a squared minus 2ab plus b squared. And I bring these things up because when we get to unit normal vectors, and the other topic that we're going to be looking at is what's known as arc length and curvature. It will be very beneficial to know these things so we can get rid of a square root. Arc length, I will tell you now, involves an integral. So if you just had this problem, so just this part right here, and you wanted to try to integrate that with a square root, good luck. But if you can get rid of the square root, then I think things will be very, very happy. You can integrate term by term, but what's hindering us is that darn square root. So if we can get rid of this by using these special factors, we'll be in good shape. So I want to take this 4t squared plus 16 plus 16 over t squared, and I want to try to use one of these special factors and rewrite it so that I have, probably going to be this first one because everything here is an addition. We're going to have a plus b quantity squared, and if I have a quantity squared with a square root, they cancel out. Intermediate step, we will have absolute value, but in the long run, they will cancel out. Okay. There are a couple ways to do this. If you would like to take out a common factor of, let's say, 4, you can certainly do that. Maybe I'll do that just so you can see the greatest common factor. So if you take out a 4, we'll end up with a t squared plus, we'll still have a 4 here, plus a 4 over a t squared. This 4, though, this multiple, is still going to be under the square root, though. I'm just taking care of what's underneath the square root at this stage. Okay. I can rewrite this as being 4 into a t squared. I can rewrite this portion here as being 2 over t, that whole thing squared. And I'll put another parenthesis here just to conclude that. And then in the middle, I can rewrite this as being 2t times 2 over t. And I'm writing it that way because I want to clearly identify that this is going to be my a, my t is my a, and my 2 over t is my b. So trying to rewrite this in this form, this portion here gives me my a, this portion gives me my b, and if I take 2 times ab, this portion here, I'll end up with a 4 because the t's will cross cancel. So hopefully you see that breakdown. With this, I can now clearly see that this is going to be 4 into, just following this template with special factors, this will be t plus 2 over t quantity squared. Very nice. So I'm going to rewrite this here. This will be, numerator stays the same, 2t, 4 over t. And I'll rewrite this as being square root, put this in colors, so you all see this. It would be 4 into t plus 2 over t, that quantity squared. So hopefully that breakdown makes sense. Hopefully you recall these special factors from algebra and everything makes sense. Okay, now we continue on with simplifying. So we'll have 2t, 4 over t. We're going to divide this by, okay, we have products in here, so we can split things apart. So square root of 4, 2. The square root and this quantity that's being squared as an intermediate step will have absolute value of t plus 2 over t, okay? But of course here, everything is positive because we started off with this restriction. So this will be 2t, comma, 4 over t divided by 2 into t plus 2 over t. And we can simplify this a little bit further. So I have another sheet. Handy. Okay. So I'm going to rewrite this as being a scalar multiple. Okay. So I can rewrite this as being 1 over 2 into t plus 2 over t. Scalar multiple 2t, comma 4, comma 4 over t. There it is. There are a couple ways you can proceed with this. If you want to distribute out this 2 here and find an LCD, we can certainly do that. So maybe I'll do that just for the heck of it. So I'll do this here on the side. 1 over, this will be 2t plus 4 over t. Distributing out the 2. LCD is obviously t, so this will be 1 over 2t times t over t plus, t over t rather, there we go, t over t plus 4 over t. Okay, so just finding an LCD, I'm just multiplying this quantity by t over t because that's the LCD. So this will be 1 over 2t squared plus 4 over t, and of course dividing two fractions, multiply by reciprocal, so we'll get t over 2t squared plus 4. So if you want to replace this part with this, you certainly can, and then just distribute things out. That's totally fine. Okay, so we'll end up with, okay, we'll have this t over 2t squared plus 4 times 2t, comma, t over 2t squared plus 4 times 4, comma, t over 2t squared plus 4 times 4 over t. Oh, I didn't budget enough room. Okay, there it is. So that's the distribution. I think we can simplify things out just a little bit further. This will be 2t squared over 2t squared plus 4, comma, 4t over 2t squared plus 4, comma, what's nice here, the t's cancel out, so you're left with 4 over 2t squared plus 4. And I think we can do a little bit more simplification. If you notice here, in these denominators, we have a common 2, so you can pull those out. This would be 2t squared over 2 into t squared plus 2, comma, 4t over 2 into t squared plus 2, comma, 4 over 2 into t squared plus 2. There it is. And 2's drop, so we'll end up with t squared over t squared plus 2, comma, let's see, 2, this goes to 2 here, because it's a common factor of 2. You get 2t over t squared plus 2, and same deal here, this will be 2, that'll be a 1, so we'll end up with 2 over t squared plus 2. As I've alluded to before, depending upon the problem, the algebra can get a little bit involved. So, just want you to be prepared for the amount of algebra that we might have to do with some of these problems. But if you work it out step by step, you should be okay. But again, the key idea behind this problem was to take a look at those special factors and try to eliminate out that square root, which will be very, very important when we get to curvature, unit normal vectors, and arc length. So that's going to be coming up. Okay, I have one more example to show you, and hopefully this will make some nice connections to concepts that we have looked at. Okay. So, last example for today. Find unit tangent vector and then find a set of parametric equations. So we know how to do that, parametric equations, for the tangent line to this r of t. So we have a 2 sine of t, we have a 2 cosine of t, and we have this 4 sine squared of t at this point of 1 square root of 3 and 1. Okay. So, a little bit of a review. If we want to figure out a line in 3-dimensional space, of course, we need a point that's on the line. We have it. And we need one more thing. We need a direction vector. Of course, with the direction numbers. But now our direction vector is going to be given by this t of t. So those are the two things that we're going to need. Okay, let's do it. Let's do it. Recall that t of t is equal to r prime of t over magnitude of r prime of t. There it is. So let's start taking some derivatives. Okay, so derivative of 2 sine of t, that's going to be 2 cosine of t. Derivative of 2 cosine of t, that's going to be minus 2 sine of t, or really I should have said negative 2 sine of t, but it's all right. Now this one, I think we're going to have to use a little bit of chain rule on this, because this is sine being squared. So we bring down the 2, so 2 times 4 is 8. Leave the sign by itself, reduce power by 1, so this is now being raised to first power. And we take the derivative of sine, which is cosine of t. A little bit of a review of chain rule. We're going to divide this entire thing by the magnitude of this. Okay, so we're going to have, let's say, a big square root. We'll have 2 cosine of t squared plus this negative 2 sine of t squared plus this 8 sine of t cosine of t squared. Okay. That's our setup. Let's simplify this as much as we can. Okay, numerator stays the same. So 2 cosine of t minus 2 sine of t, 8 sine of t, oops, this should be cosine of t. There we go. Divided by, let me wipe that out. That's kind of bothering me. I don't like that little mistake I made there. Okay, there we go. That's better. Whiteout helps, especially when you're writing in pen. Okay, square root of, we're going to have 4 cosine squared of t plus 4 sine squared of t plus, now we need 8 squared, so that's going to give us 64 sine squared of t cosine squared of t. Hopefully the algebra all makes sense with laws of exponents, all that fun stuff. Okay, numerator is the same, so we'll have 2 cosine of t minus 2 sine of t, 8 sine of t cosine of t divided by okay, let's see, what can we do? We can definitely take out a common 4 from these first 2 terms, and we can even take it out from this term as well if you like, but I'm just looking at this and saying, well, if I take out the common 4 from these two, I'll have cosine squared of t plus sine squared of t. That's going to give me 1, but we can also take out the common 4 from everything, which would be fine. But maybe I'll just do it in steps. So we take a 4 out, we'll have cosine squared of t plus sine squared of t plus this 64 sine squared of t plus, no, not plus, multiplication, sorry, multiplication, cosine squared of t. There it is. And of course, this portion here gives us a 1, which is really, really nice. So we'll end up with 2 cosine of t minus 2 sine of t, 8 sine of t cosine t. There it is. And we divide this by, this is going to be a 4 plus the 64. So what I could do, I could write it this way, and hopefully you all agree with me. This will be 4 into 1 plus, now if we take out the 4 from this, 64 divided by 4 is going to give us 16. So it would be 16 sine squared of t cosine squared of t. And of course, you have products in here, so square root of 4 gives us 2, and then we'll have the square root of this stuff, which I don't think we can do much else to this. So I think we'll leave the answer as being, I have another sheet of paper in here, I think we'll leave this answer as being the following. So we'll have 2 cosine of t, comma, negative 2 sine of t, 8 sine of t cosine of t. We're going to divide this by 2 square root 1 plus 16 sine squared of t cosine squared of t. I don't think we can do anything else with that, at least not with what I'm seeing. I mean, could you do the scalar multiple? Yeah, you could, but is it really going to contribute much to anything? Not that I can see. So we'll leave it as unit tangent vector to be this. Okay, it's a little bit complicated, but we have it. Okay, so now that we have our t of t, we need to substitute in the t value that represents this point. Because notice here, this is in the terms of x, y, and z. We need the parameter t that represents this. Because remember, this is all with respect to t. So how can we get that? Well, we can take one of these coordinates. I don't know, I'm kind of lazy. How about the first one? And we can equate it to the first component of the r of t. So we'll have 1 equal to 2 sine of t. And if we can solve this thing out for t, we'll have the parameter value t that represents this point. So start by dividing both sides by 2. You'll end up with sine of t equal to a half. And let's see, going back to the unit circle, or if we do a 30, 60, 90 right triangle, I think the t that will fit this description is pi over 6. So sine of pi over 6, if you guys remember. Here is your 30, 60, 90 right triangle with your two legs being 1 and square root of 3, hypotenuse being 2. This angle right here, this is 60 degrees or pi over 3 radian measure. This is 30 degrees or pi over 6 radian measure. We want the sine, so if we take the sine of pi over 6, 1 over 2, we get it. Okay, so let's put this in, and let's see how this thing shakes out. So t of pi over 6. Okay, so we'll have 2 cosine pi over 6, comma, negative 2 sine pi over 6, comma, 8 sine pi over 6, cosine pi over 6. We're going to divide this by 2 square root 1 plus 16 sine squared of pi over 6 cosine squared of pi over 6. Just looking at this thing now, I guess we could have also have canceled out the common factor of 2 everywhere, but this is fine. We just have to figure out what this thing is going to be. We'll have our direction numbers, we have our point of interest, and we can construct the parametric equations. Okay, let's do it and see what we get. So we need the cosine of pi over 6. So we can go back to this 30, 60, 90 right triangle if we want. This is going to be 2 times square root of 3 over 2, negative 2 sine of pi over 6. We know that that is a half. So this will be multiplied by a half. We have this 8 sine of pi over 6. It's a half. Cosine pi over 6, square root of 3 over 2. Divide by 2 square root 1 plus 16. This will be half squared, and this will be square root of 3 over 2 squared. Hopefully that makes sense. So here, 2's cancel, 2's cancel. This is going to be 8 divided by the 4, so we're going to end up with a 2 here. These will all cancel out. So let's see, we're going to get on the top square root of 3, negative 1, and this will be 2 square root of 3, divided by 2 square root 1 plus 16. This will be quarter. This will be 3 over 4. Okay. Let's see. This will be square root of 3, negative 1, 2 square root of 3, divided by 2 square root 1 plus, let's see, 16 divided by these two 4's here. Gonna cancel everything out except the 3. So this should shake out to be square root of 3, negative 1, 2 square root of 3 over 2 square root of 4, I believe. So this square root of 4 is 2, so you'll get a 4 in the denominator. So you'll get square root of 3, comma, negative 1, comma, 2 square root of 3 over 4, if you like. And if you want to rewrite this, you can, of course, do a scalar multiple. So you could say it's this, square root of 3 over 4, comma, negative 1 over 4, comma, 2 square root of 3 over 4. And then, of course, this can be simplified to be square root of 3 over 2. But let's stop for now, because we could simply take these as your direction numbers, because we have this a quarter as being a scalar multiple of this. So again, if you guys remember when I was talking about how parametric equations are not unique, you could write the answer this way. So we got x equals, y equals, z equals. If you want to use these as your direction numbers, you can. So you'll have square root of 3 over 4t, negative a quarter t. I'll simplify this. This will be square root of 3 over 2t. And of course, just tack on the point. The point was 1 square root of 3 and 1. So we'll have plus 1 plus square root of 3 plus 1. This is a totally acceptable answer. But you could also use these as your direction numbers and write it out this way. So I'll put this as an OR here. X, Y, and Z. You could write this out as being square root of 3, be negative 1 there, be 2 square root of 3 here. And just to give this a distinction, maybe we can use another parameter, maybe call it S or something, or T sub 1 if you like, and then put in the points. Plus 1, plus square root of 3, plus 1. This would also be another acceptable answer, because one of them deals with the simplified version with the scalar multiple, but the other one doesn't. These two represent the exact same equation of a tangent line to whatever this thing is in terms of sines and cosines. I don't know what it looks like. I could probably graph it for you on a computer algebra system, but either one of these would represent the exact same tangent line. The only difference is that this one you're using this set of direction numbers, which has the extra multiple of a quarter multiplied through, but this one doesn't. But either one of these will be totally fine. I beg and I plead, please only just give me this answer. That would be great. If I do ask you for this one, I will tell you which one I want for my ease of grading. So I think that's a nice introduction. Hopefully you all have a good rest of your day, and I will see you back next week. Bye-bye, everybody.